the third and final part of this lecture, we'll be learning about ocean acidification, and I'll leave it to you to read through the learning objectives as usual. The diagram on the left here shows the carbon cycle with the addition of anthropogenic carbon dioxide emissions into the atmosphere from fossil fuel burning and the additional uptake of CO2 into the surface ocean due to the increasing CO2 in the atmosphere. The plots on the right here show that increase in CO2 in the atmosphere, here in red, from around about 1980 up until almost the present. And you can see here that in the surface ocean, the PCO2, or the fugacity, the FCO2, carbon dioxide in the surface ocean is closely following the trend in the ocean upwards as the surface ocean tries to maintain its equilibrium with the atmosphere. At the same time as the dissolved CO2 is going up in the surface ocean, we can see that the pH, shown in black here, is decreasing. So we've had a decrease in the surface ocean pH from over this time period of around about 25 years, from about 8.12 pH units in this particular location down to around about 8.08. Now that might not seem like a very large decrease, but you have to remember that this is a log scale and the corresponding absolute decrease is really quite significant. The other thing I'd like to draw your attention to is this decrease in the carbonate ion concentration. And so when we have acidification of the ocean, decreasing pH, we also have this reduction in the carbonate ion concentration. And as I'll show you, it's this concentration of carbonate ion that's particularly important for marine calcifiers and explains why they are at particular risk from ocean acidification. So this diagram sets out schematically the exchange of CO2 between the atmosphere and the ocean, and then the reaction of CO2 with water in the ocean to produce carbonic acid, a diprotic acid that has two hydrogen ions here, or two protons. That carbonic acid dissociates in seawater to produce bicarbonate ion and a proton, which makes the ocean more acidic. That proton that's released here drives this other reaction, the equilibrium between bicarbonate and carbonate ions. It drives it back to the left. So I've written out those reactions here, and I'll leave that to you to read through that. And over on the right here for the chemists, we have the equilibrium constants that one can use to calculate the equilibrium between all of these species. This plot on the left here shows that calculation going from a pH of 0, so highly acidic, through to highly alkaline, and the change in species that occur as the pH increases or decreases, becoming more acidic in this direction. So you can see that the carbonate ion dominates at high pH, but as the pH becomes lower and the ocean becomes more acidic, carbonate ion concentration decreases and the bicarbonate ion increases at the same time, and eventually at much more acidic conditions which the ocean won't reach, even the bicarbonate ion reduces and carbonic acid and CO2 become the dominant species. This is a blown up section of this diagram here, and this shows the current sea surface pH around much of the ocean and the sort of change that is expected for the surface ocean over the coming decades and centuries. So we'll be seeing a reduction in the pH, and as that reduction occurs, carbonate ion here is going to reduce significantly. Those reactions are set out here in this nice little diagram. Carbon dioxide dissolved from the atmosphere reacts with water to produce carbonic acid, which dissociates to produce bicarbonate ions and hydrogen ions, or protons, making the ocean more acidic. Those protons then react with carbonate ions in the ocean to produce more bicarbonate ions. So that's effectively this reduction in carbonate ions, increase in bicarbonate ions, and at the same time a reduction in the pH. Now, if we look at the change in surface ocean pH produced by anthropogenic CO2 emissions since the pre-industrial period to about the 1990s, we can see this sort of distribution where we have the ocean becoming significantly more acidic in these high latitude regions, high latitude North Atlantic and in the North Pacific, with smaller changes, although still significant, in the tropical regions. So here we have the relative reduction in pH units, noting that a reduction of 0.1 pH units is actually a 30% increase in the abundance of protons or hydrogen ions in the ocean. So what happens to the surface ocean pH if atmospheric PCO continues to increase and doubles from those 1990 levels up to around about 800 ppm, which is quite a reasonable estimate for where we could end up if we burn a very large amount of our available fossil fuel reserves. So you can see here at 350 ppm, which was the atmospheric concentration of CO2 in the 1990s. If we continue on through to 800 ppm carbon dioxide in the atmosphere, we'll see a continuing reduction of pH in the ocean of between 0.3 and 0.35 pH units relative to the 1990s. As you can see here, under colder temperatures, because more CO2 can dissolve in seawater at colder temperatures, the pH effect is even more significant at lower temperatures in the high latitude oceans. This diagram shows sections of the ocean showing the uptake of anthropogenic CO2, or the amount of anthropogenic CO2 in micromoles per kilogram of seawater throughout the ocean basins. And you can see that it's mainly restricted to the upper 1,000 metres or so of the ocean, so near the surface, as you might expect with the exchange between the surface ocean and the atmosphere. But you can see also that here in the high latitude North Atlantic, you start to see the North Atlantic deep water formation in that region already beginning to bring anthropogenic CO2 into the deep ocean. And it's a little bit off the side of this plot, but you can just capture the Antarctic bottom water also bringing in CO2. Now, this deepening of the CO2 uptake here is related to that Antarctic intermediate water moving north and being subducted below the lower density surface waters moving south in this area. So this is also bringing higher CO2, anthropogenic CO2, into the upper part of the ocean. A recent analysis of the uptake of anthropogenic CO2 has shown that there's been a surprising increase in the ocean inventory of anthropogenic CO2, which they call CANT, in the 15 years between 1994 and 2007. The importance of that is the ocean uptake is slowing the CO2 accumulation that would otherwise occur in the atmosphere, but this is obviously then occurring at the cost of increased ocean acidification. And their plot, which is an update from the previous figure on the other page, noting that this is 0 to 500 metres and then the scale increases. So this is then 500 to 4,500 metres. So it's not exactly a linear scale, but it shows that ocean acidification and the uptake of anthropogenic CO2 is now reaching deep into the ocean interior. And you can see that effect on this diagram where all of this blue water represents the North Atlantic deep water entering the mid-depth area within the North Atlantic. And you can also see the Antarctic bottom water taking anthropogenic CO2 deep into the Southern Ocean as well. So what's the impact on life in the ocean? We have a whole group of organisms known as marine calcifiers that include corals, molluscs, coccolithophorids, which are a phytoplankton group, foraminifera, which are calcifying zooplankton, and then the pteropods, which are these free-swimming planktic molluscs. Now, all of these organisms extract carbonate ions from seawater and calcium ions from seawater to form their skeletons and shells, and that's represented here by these diagrams where calcium plus carbonate ions extracted from seawater to form solid calcium carbonate. Interestingly, there's a similar cycle to the organic carbon cycle where this particulate calcium carbonate sinks into the deep ocean, and then because the solubility of calcium carbonate increases in the deep ocean, that tends to redissolve and return to the original dissolved calcium and carbonate ions, which are then able to return back to the surface ocean. Shown on the left here is the fugacity of CO2, or the parts per million of CO2 in the surface ocean, and showing how that as this value increases, that the pH decreases. pH scale is here on the right. And at the same time, the carbonate ion concentration decreases as this CO2 level goes up in the ocean. Now, the reduction in that carbonate ion then makes it more difficult for these organisms which need this ion to form their shells. So the less of this that's available, the harder it is for these organisms to form their shells and skeletons. This just gives you an overview of some of those organisms that we've been through. Another concept here that's quite important is the saturation state of calcium carbonate in the ocean. So those of you who are doing chemistry may be aware that you can write an equilibrium solubility product for this reaction here, where calcium ions plus carbonate ions form calcium carbonate, and this has a particular constant value that one can use to define the concentrations of calcium and carbonate ions that you need in seawater, in this case, to be able to precipitate calcium carbonate. We can use this equilibrium solubility product by measuring calcium ions and carbonate ions in the ocean, multiplying the product of those ions and then dividing it by this equilibrium solubility product, and that gives us the omega, or the saturation state of the ocean with respect to calcium carbonate. If this value is greater than 1, i.e. when carbonate ions are high, this value of omega is going to be higher. Water is supersaturated and calcium carbonate can precipitate. When carbonate ions are low, then the omega value can be less than 1 and the water will be undersaturated and calcium carbonate will dissolve. Over on the right here, we have some projections for the surface ocean going out to the year 2100 for the saturation state omega of 2 different forms of calcium carbonate, calcite, which is formed by foraminifera and also coccolithophorids and some molluscs, versus aragonite, which is another form of calcium carbonate produced by corals and other molluscs. And you can see that by the time we can see a reduction in the carbonate ion in the surface ocean to the point where by around about 2060 to 2100, subject to the atmospheric CO2 levels of these different projections or CO2 emission scenarios, we end up with an ocean that's undersaturated at the surface with respect to aragonite, which is that main form of calcium carbonate used by corals. People have done this sort of modelling extensively and can show that over a period of several centuries, the surface ocean pH is likely to reduce by as much as 0.7 pH units, which is almost an order of magnitude reduction, which will result in almost an order of magnitude reduction in carbonate ions and increase in proton concentration in the ocean. So these are just a couple of different scenarios for burning different amounts of fossil fuel carbon between 1,000 and 5,000 petagrams, and then the resulting carbon dioxide concentrations in the atmosphere and surface ocean pH changes. So to finish up now, here we have the cold Southern Ocean. Because CO2 is much more soluble in colder water, the effects of ocean acidification are most significant in these high latitude waters. These little plots here on the right show the saturation state as a function of depth going from the North Atlantic to the south. You can see this whole part of the Southern Ocean here, depths below 1,500 metres, becomes undersaturated with respect to aragonite, this particular form of calcium carbonate that's used by corals and also by these pteropods, these free-swimming molluscs in the ocean. Now, the projection by 2100 then is that virtually the entire Atlantic Ocean, almost up to the surface in the southern hemisphere, and then almost to the surface throughout the rest of the Atlantic Ocean, becomes undersaturated with respect to aragonite. These little molluscs live mainly in the surface ocean down here, and they're an important food source for whales, and experiments have shown that these little guys find it extremely difficult to form their little shells and are unlikely to be able to survive in these more acidic and aragonite calcium carbonate undersaturated waters. On that not so positive note, that's the end of our exploration of the oceans in weeks 10 and 11 of the Blue Planet. Let's hope that's not the end for the oceans, and I do hope to see many of you at One Tree Island on our EMSC3023 field trip, which we run up there every year.